Swayam Prabha. Digital India. Educated India.
So, in last class I have discussed about the different types of shear modulus, that is Gmax, maximum shear modulus, then the second shear modulus, tangential shear modulus, and then in linear model we will use the Gmax, equivalent linear model we will use the Gsec, and for non-linear model we will use the Gtan. Okay, and then I will also discuss the how to calculate the damping ratio. Now today this class I will first discuss how we will determine the Gmax value, and then I will discuss how we will get the G value, Gsec, by using at different strain level. So this is the Gmax value. So that means that is for that initial portion of the stress strain curve. The tangent, if I take a tangent in the initial portion of the stress strain curve, I will get the Gmax value. In addition to that, by using this empirical expression, I can determine the Gmax value by using laboratory test data as well as the field test data. So that means first shear Gmax value, the expression is proposed by Hardin and Drenovich. So this is not the first expression, this is I am explaining, this is the first expression. So that means this is Gmax corresponding to shear strain less than 0.25 into 10 to the power 4 or 0.25 10 to the power minus 2%. Okay. So that is for this Gmax, this is the expression. Where is the void ratio? OCR is the over consolidation ratio. K is an over consolidation exponent, and that K value I will get from this table. That K value is function of plasticity index Pi. If Pi is 0, K value is 0. If Pi is 40, K value is 0.3. If Pi is 80, K value is 0.48, and if it is greater than 100, it is 0.5. Okay. Similarly, the sigma m is your mean effective overburden pressure. That means it is summation of sigma 1 dash plus sigma 2 dash plus sigma 3 dash divided by 3. So generally the sigma 1 dash is the vertical effective overburden pressure, and sigma 2 dash plus sigma 3 dash are the horizontal effective pressure or horizontal stress. Now n is the stress exponent and can be taken as 0.5. So this expression is valid for both sand and clay, and here your mean effective stress and the Gmax are both in pound per inch square. So remember that if you use this expression, you have to consider this unit only. This is the empirical expression. Okay. Next one, and this is the reference of this Hardin and Drenovich. So this is the reference. Next one, Gmax can also be determined by this expression, which is similar to the previous expression. Difference is that the F is a function of void ratio. Pa is the atmospheric pressure, the same unit at Gmax and sigma m dash. That is Gmax, sigma m dash and Pa should have same unit. Suppose for example Pa in kPa it should be 100 kilonewton per meter square if provided the Gmax and sigma m dash are also in kPa. Clear? Hardin proposed that this F function is equal to 1 by 0.3 plus 0.7 E square is the void ratio. Another proposal is that F is 1 by E to the power 1.3. So this way also I can determine the Gmax. Then I can determine the Gmax by using this expression. So from where I will get the Vs? So I have discussed my the low strain field test, where I will get what? I will get the your Vs or Vp. If you get the Vp, then also you can determine the Gmax, provided you have to know the your Poisson ratio of the soil along with the density of the soil. But if you determine the Vs, velocity of shear wave, then if you know the density of the soil, then you can get the Gmax. So because those are low strain tests, so that will give you the Gmax. Then Gmax can also be determined by SPT CPT data. Though the SPT CPT are large strain tests, but the property that they will get, that is the, by using these correlations, that will also Gmax. Okay. So that means Gmax can also be determined by SPT CPT data as well as your DMT data also. So that means this is my first expression of Gmax, which is N160, and I have already discussed what is N160. 60 is a 60% hammer efficiency. 1 means that it is normalized by 1 ton per feet square or 100 kPa. Okay, and this is 0.33 to the power sigma m dash to the power 0.5. So this SPT, this is valid for the sand. Okay, and here as these are also empirical expressions, so this unit should be pound per feet square. Then the CPT data for sand, quartz sand, it is this is the expression where sigma V is the vertical effective overburden pressure, and again the Gmax QC is the cone resistance, and sigma V dash are in kPa. I have also discussed what is cone resistance. Then for CPT data for clay, then we can use this expression. Here also Gmax and QC are in kPa. Okay, and E is the void ratio. Okay, so now and QC is the your cone resistance. Now the Gmax can be determined from DMT, dilatometer test data also. Here you can use this expression Gmax by ED. ED I have discussed what is ED. So there also you will get with some plus minus, this range is given, and this is for sand, and for a normal expression or general expression is given that it is Gmax by ED is 0.75 for KD is equal to 1.5 to 2, and it is equal to 2 for KD greater than 5, and generally KD2 it is indicates the normally consolidated clay. So that means the first one is valid for clay, and second one is also close to this expression, so that is valid for sand. So but you can see that what is KD, ED I have already explained. So the in my previous lectures, so that you will get from the how you know how to get the KD and ED. So you get the KD and ED, and then you can use this expression, you will get the Gmax value. Okay. Now I will first discuss about the how to, now I know how to determine the Gmax, but now I don't know how to determine the G value at any strain, because as I mentioned, if it is in high strain condition, so your G is also function of strain and G value will decrease with strain. Okay, and for earthquake analysis, for earthquake case, we have to use either equivalent nonlinear approach or equivalent linear approach or nonlinear approach, because we have to consider the reduction of the G with strain. Okay, so now first approach that is that I will discuss, this is also equivalent linear approach. Okay, so this is also an equivalent linear approach, so that is proposed by Hardin and Renovich. So here suppose this is your backbone curve. Okay, so I am drawing only the half portion of the backbone curve. This is shear strain, this is shear stress. So say this is backbone curve. So, the initial slope that will give me the G max. Okay, and at any point, now from this point onwards, G value will change. So, if I want to take it is a equivalent linear approach. So, at any point, if I want to determine the G value, I have to join this point and the origin, and slope will give me G sec. Okay, and then this is backbone curve, and then if I join the or draw a line from this point. So, this will give me the maximum shear stress, that is the tau max. This is the maximum shear stress, tau max. And if I join this initial state portion where it will cut the tau max, corresponding strain is taken as reference strain. That means this is my strain reference, so that the coordinate of this point will be tau max, or I should say if the x coordinate or the y coordinate will be the tau max and the reference strain, this point. This point the strain level is reference strain and stress is tau max. Now, for linear model, you know that for the linear case, your G or the your G max or the G is G is shear stress divided by shear strain, or your tau will be simple G into shear strain, shear modulus into shear strain. But here for equivalent nonlinear case, this backbone curve is being simulated or represented by these expression. This is, or you can say this is tau into G max by shear strain. Okay. Now, here it is been represented by G max into shear strain, same as linear model, but divided by 1 plus G max by tau max in shear strain. So, this is now my stress strain relationship. For linear it is simple, tau is equal to G max into the shear strain. Shear stress is equal to G max into shear strain. But now for this equivalent linear model, the relationship to represent this nature of this curve, so it is given that tau is equal to G max into shear strain divided by 1 plus G max into shear strain divided by tau max. What is tau max? Tau max is the maximum shear stress. Okay, and G max is the, you know, that is the linear straight. If I draw a slope along the initial linear portion, I will get the G max, and I have already discussed how I will get the G max value. Okay, now if I write this thing, then one more thing from here, if I draw this curve, then I can write that my G max, I can also write like tau max by strain reference or reference strain. I can write that because this is my reference strain and this is G max. So, that means this will be definitely tau max by reference strain, I can write. Now, if I write that and I know that my tau is equal to G max into shear strain divided by 1 plus G max into shear strain divided by tau max. Okay. Now if I replace the tau max equal to G max by reference strain. Now if I replace the tau max, so I will get G max into shear strain 1 plus G max divided by G max into reference strain into shear strain, reference shear strain. So now if I G max will cancel, so this will be simple G max into shear strain 1 plus shear strain divided by reference strain. This is the expression. Or I can write that tau is equal to your, or I can write that this is tau divided by shear stress divided by shear strain, and this is G max 1 plus shear strain divided by reference strain. Now shear stress by shear strain at any point will be what? Shear stress by shear strain at any point will be the shear modulus G, but that will not be the G max. G max is the initial one, but now it is the shear strain at any point or any strain level. So that is your, or any point on this backbone curve. So that will be G, and this will be G max. Now this is 1 plus strain H. What is strain H? Strain H is nothing but shear strain by reference strain. Okay. So that is the expression I will get. So this is the expression that is given. Now one more thing, that when we are, this is okay. So now we will get the shear, if I know the maximum shear modulus, and if I know the shear strain H or the shear strain reference strain, then I can determine the shear modulus at any strain level. Okay, but as it is basically that the expression is proposed in such a way that we can simulate this backbone curve accurately, or we can generate this backbone curve accurately by using these expressions. So it is observed that if I write, or if we write that tau strain H by a hyperabolic relationship, then this equation can simulate this curve in better way. Okay, so that's why this strain H is further written in this form. Okay, in addition terms are 1 plus A e to the power minus B into strain by strain reference. So that means it is actually this is the strain H, that is strain divided by strain reference, but it is observed that if I represent this strain H in this form, then this equation can simulate this curve in better way. Okay, so this is for, I will discuss how I will get the A and B, those two parameters through a table. So now what are the things I have to determine? First you see, I have to determine A and B, then strain at any strain level I will get that value, and strain reference, all these things I have to determine. So now this is for shear modulus. Similarly for damping ratio, also damping ratio is equal to D, say D max. D is the damping ratio at any strain level, D max is the maximum damping. Okay, so sorry, this is D by D max only, this is not D by D max. So this is equal to 1 minus G by G max, which indicates that if G is equal to G max, then this D by D max, I mean your damping ratio is equal to maximum damping if your G is equal to G max. Okay. So your if your G equal to G max, your D is equal to will be 0. So that means that for low strain condition, your shear modulus is maximum, and as strain increases, the shear modulus value decreases. But damping, it is opposite, that the low strain level, the damping is lowest. As the strain level increases, your damping value will also increase. Clear? I will show you the trend. My equation is also showing that. Suppose if your G is equal to 0 theoretically not possible, but say, I mean practically is not possible. If you say G equal to 0 or very small value, then D will be equal to D max, that means the maximum damping. D is the damping at any strain level. So if you say that your G is equal to G max, that means the initial point, low strain condition, then your damping will be 0. But if your G is very small or close to 0, then damping will be maximum. So that means the shear modulus is highest at low strain level, but as strain increases, modulus value decreases. But for damping, it is for low strain level, it is but in case of damping, the damping value increases as strain increases, but shear modulus value decreases as strain increases. Clear? Now this is the equation. So now I can write that here it is 1 minus G by G max. So now I can replace this G by G max. G by G max is 1 by strain H. So G by G max is basically 1 plus strain H. Okay, or you can write that this is equal to strain H divided by 1 plus strain H. Here also we can represent this strain H in this way, that this is shear strain divided by shear strain reference, and 1 plus A1 e to the power minus B1 strain divided by strain reference. Okay. So here also I will get this, how will I get the A1 and B1 parameter. So I will get the A1 and B1 value. So for damping it is A1 and for modulus it is A, for damping it is B1 and for modulus it is B. So this table is given. So for clean dry sand, for A value will be minus 0.5 and B value will be 0.16 and damping will be 0.6 n to the power minus 16 minus 1, where what is n? N is the number of cycle. That means you will take the soil sample and you will do the test, and you will apply the number of cycle, this cyclic load. So the n value is number of cycle. Okay, and similarly for clean saturated sand, you will get these. You can use these two expressions to get A, B and A1, B1 for damping, AB for modulus. Then saturated cohesive soil, you will get this expression here. Another term is there. If it is log, means log base 10. So if it is F is where? F is the cycles per second. Okay, and N is simple the total number of cycle. And sigma 0 bar is the initial effective overburden pressure, that is in kg per centimeter square. So you have to use this expression, this unit only, kg per centimeter square. Now similarly, another table is given to give the D max, maximum damping in percentage. How I will get that? Okay, so soil type and this is again the clean dry sand, clean saturated sand, saturated seal, various saturated cohesive soil. So, and this is Dmax in percentage. For clean dry sand, it is Dmax is 33 minus 1.5 log n. N is again the number of cycle, but F is the again cycles per second, and sigma 0 bar is again kg per centimeter square. So, the initial effective overburden pressure. So, if I use this expression, I will get the Dmax, and if I use this table, then I will get the A, B and A1, B1. Clear? Now, let us solve one problem, then we will get this, then you will understand how I will get the shear modulus at any strain level. So, what is the problem is given? Determine the shear modulus and damping ratio at a depth of 5 meter below ground level for the following soil layer in the 7th cycle. That means total 7 number of 7 cycle it is we have to determine. I don't know how many cycles are being applied, but I have to determine what would be the shear modulus and damping ratio at 7th cycle, okay, on that soil which is taken at 5 meter below the ground level. At strain level our 7th cycle is 0.15%. So, that my strain level, this is strain is 0.15% or 0.15 into 10 to the power minus 2. That is strain level is given. And K0 is 1 pi minus sin phi. Use equivalent linear model proposed by Hardin and Drenovich 1972. So first let me first write those expressions. Now, what are the things I have to determine? So, I have written, you know, that G is equal to G max 1 plus strain H, okay, and for this is for modulus, and strain H for modulus is strain by strain reference 1 plus A e to the power minus e to the power minus B anyhow, this is e to the power minus B strain by strain reference. So, if I write this is B actually, okay. So, and then strain reference is what? Strain reference is your tau max by G max, okay. So, what are the things first for the modulus part? Let me discuss about the modulus part. So, I have to determine what are the things I have to determine. I have to determine the G at a strain level of 0.15 into 10 to the power minus 4 at minus 2. So, that strain level I want to determine the G value because as I have shown that G will change with strain and obviously G value will reduce as strain level increases. So, here G should be less than the G max obviously, but in case of damping it is opposite. So, what are the things I have to determine? I have to determine G max, okay. Now, this A and B I will get from the table. So, strain is given. So, I have to determine strain reference. So, to know the strain reference, I have to determine tau max also. So, to know the strain reference, I have to determine G max and tau max. Also, I have to determine the G max to determine the G value. So, let us first determine the G max value. First determine the G max value. So, I will use the expression proposed by this. Before that give me that soil layer condition. So soil condition is that this is your ground surface GL and water table is at 2 meter below the ground surface and at 5 meter below the ground surface. That means from the water table the point is say A, which is another 3 meter. So basically from the A the sample is taken and then it is been tested. It is observed that for 7th cycle the strain is 0.15%. Now I have to determine what would be the strain, shear modulus and damping at that strain level under 7th cycle. So the other properties are given that for gamma bulk on the unit weight above the soil layer, water table is 19 kilonewton per meter cube and gamma sat is 20 kilonewton per meter cube and gamma W is taken as 10 kilonewton per meter cube. Okay. Phi value, it is a sandy soil, phi value is given 38 degree, C value is 0 and it is E value is 0.5 and it is normally consolidated soil or NC soil. Normally consolidated whose E value is 0.5, phi value is 38 degree, it is sandy soil. So now first we will get the Gmax value. Okay. So how I will get the Gmax value? I will use this 1230, the first expression of Gmax that I have given, because those data are available. If it is the SPT value is available, then you can use those correlations. So I have given few of the correlation. There are number of correlations are available by using those SPT, CPT, DMT data or pressure meter data. So now, but here this is the E value is given, so I will use this expression. Okay. So the first expression, if it is SPT is given, you can use the SPT expression to get the Gmax. So here this is your 2.973 minus E to the power square divided by 1 plus E into OCR to the power K and sigma m bar or dash to the power 0.5. That is the expression was given, the first expression that is given. But remember that here your Gmax and sigma m bar are, this is pound per feet square. Okay. Now if I convert it to both Gmax and sigma m bar kilonewton per meter square, then the equation will change. This equation will be your 3230 2.973 minus E to the power square 1 plus E OCR to the power K sigma m bar to the power 0.5. So in this equation your Gmax and sigma m bar are in kilonewton per meter square or kPa. That is that unit I will use, because other parameters are given in kilonewton per meter square. That's why I have converted it to kilonewton per meter square. Okay, so now this Gmax OCR value is what? OCR value is equal to 1 because your normally consolidated soil. So your E value is equal to 0.5 is given. Now I have to determine the sigma m bar. Now what is sigma m bar or dash? That is given is 1/3 of sigma 1 bar plus sigma 2 bar plus sigma 3 bar. Okay. Now sigma 2 bar is basically K0 times of sigma 1 bar. Similarly, sigma 3 bar is K0 times of sigma 1 bar. Sigma 1 bar the vertical effective overburden pressure, and the sigma 2 bar and sigma 3 bar are the two laterally given effective pressure, which is the K times K0 times. K0 is the your earth pressure coefficient at rest. Okay. So K0 times of this vertical effective overburden pressure. Now where K0 can be determined by 1 minus sin phi. Okay. So this is 1 minus sin 38 degree. So K0 value is 0.384. Okay. Now what is sigma? That is sigma 1 bar is basically sigma V bar, vertical effective overburden pressure. Let me determine the sigma V bar. Sigma V bar is how much? That is at 5 meters. So it is effective overburden pressure. So for above the water table it is 2 into 19. 2 into 19, then below water table it is 20 minus 10, submerged you have to consider, into 3. So that is equal to 68 kilonewton per meter square. So my sigma m bar will be 1/3 of your sigma 1 bar is 68 plus K0 is 0.384 into 68 into 2, you can say. Okay, it is into 2 also, because this is 1 plus 2 and into 2. So that is coming out to be 40.1 kilonewton per meter square. Okay, 40.1 kilonewton per meter square. So now if I put this value here in this equation, then I will get G max, which is equal to 3230. Okay, 3230. So this is 40.1, yeah, 40.1 kilonewton per meter square. 3230 into 2.973 minus 0.5 to the power whole square divided by 1 plus 0.5, because E value is 0.5. This is 1 to the power k, that as it is 1, OCR value is 1, that's why I am not determining the k value. Otherwise you have to determine the k value from the table which is given. I have also given the table. So this is into the sigma m is your, that is 40 sigma m value, that is 40.1 to the power 0.5. Sigma m value or sigma m bar value is given 40.1 kilonewton per meter square. So that's why the G value will given that 8 G max 83393.4 kilonewton per meter square. So I have determined the G max value. G max value is coming out to be 83393.4 kilonewton per meter square. Okay. So I have converted it and I have given it in the, because now the both G max and sigma m bar are in kilonewton per meter square. Okay. So in the next class I will continue from here and I will show you that from here how I will get the shear modulus at the strain level of 0.15%, because here I have determined only G max. With the help of G max I will get the G value at any strain level. Here the strain level is 0.15%. Thank you.